we start with Aurelia, yeah. Okay, yeah.
Please,
Okay.
please, Michael.
In that, yeah.
Okay.
In that case, can I welcome everybody to this session on problems in mathematical biology, which is mainly chaired by Joaquim, who created the program. And our first speaker is Marilia Pires, from the University of Évora. And she's going to talk about the applicability of the tensorial artificial diffusion stabilization in numerical simulations of altered B-type fluids. Marilia, please.
Thank you, Michael, for your nice presentation. So good morning. I want to thank the organizer of the session for inviting me to share. As Michael said, today I would like to speak about the applicability of tensorial artificial diffusion stabilization in numerical simulations of altered B-type fluids. This work was done with Thomas Bodnar of the Faculty of Mechanical Engineering in Prague and Institute of Mathematics, Czech Academy of Science. Okay. Our motivation for this work was the hemodynamics. Although there are other range of applications like polymeric fluids or industrial fluids and materials. Among the mathematical models used to describe the blood behavior, we work with Aldroyd B equations to capture the viscoelastic characteristic of the blood. It means that the fluid has the same ability to store and recover the deformation. To obtain the numerical solution, we use the finite element method with two different stabilization technique and the discretization of Eulerian-Lagrangian type. The simulations are done in the bidimensional channel in the study case, and we analyze the limits and the robustness of the application. The test allows us to obtain some conclusions and remarks. This picture represents an example of the mechanical analogous model of the effects of different contributions in the Aldroyd B model. From the property of the viscoelastic fluids to allow them to store and recover the energy, we can define two time scales. The relaxation time scale defined by the parameter lambda1, which indicates the time during which the fluid remembers the story of its flows. It is defined by the ratio between the elastic viscosity represented here by the dashpot and the Young models, which translate the elastic effect represented here by the spring. And the other time scale is the retardation time, represented by the lambda2. This indicates the response time of the fluid to an instantaneous application of a constant tension. This is linearly related with the relaxation time by the constant of proportionality given by the ratio between the solvent viscosity represented by the other dashpot and the total viscosity. Here we can see also the effects of the extra stress tensor. Due to the memory of viscoelastic fluid, does it remember its past deformation story? Extra information is required at the inflow boundaries and to provide information about what's happened before the fluid enter in the domain. Because of all these increments, the numerical simulation of the viscoelastic fluid is very complex. In addition, the large values of the relaxation time are associated to the breakdown of numerical solution. This problem is called by Eigen-Weissenberg number problem. The Weissenberg number is a non-dimensional parameter linearly proportional to the relaxation time, as we go to see. To avoid this high Weissenberg number problem, we need a special numerical treatment. For the example, we can use the artificial stress diffusion as we done in this work. This system gives us the governing equations for the Aldroyd B model, and is constituted by the conservation, the momentum equation, the mass conservation, and the constitutive equation. Here we can see the velocity vector field. P is the scalar function, is the pressure. F is the external body's force, and eta is the non-dimensional viscosity parameter. This is called the polymeric viscosity. And assume values between 0 and 1 is part of the total viscosity. Appear here the Reynolds number, a non-dimensional parameter, which quantify the inertial effects in the fluid. Is given by the ratio between the inertial forces defined by rho and the characteristic velocity, and the viscosity forces given by the ratio between the dynamic viscosity and the characteristic length of the domain. Here we have also the strain tensor defined by the symmetric part of the gradient of the velocity. And we have in this side, this is the, 2, 1 minus eta d is the Newtonian contribution of the extra stress tensor, and the other part of this tensor is given by tau, that is known as the elastic stress tensor, and is related with the shear rate 2D by the constitutive equation, where appear the Weissenberg number, defined here as the ratio between two time scale. One for the memory of the fluid, denoted by lambda 1, and the other is the convection advection time scale defined by U over L. The total stress tensor is defined this way. Remark then that when Weissenberg is equal to 0, in fact, we have a proportionality between the elastic stress tensor and Newtonian tensor, and in this case, this system reduces the Navier-Stokes equations. To discretize our problem, we follow the root method. This means that we discretize the space after we discretize the time. We fixed the delta t as a constant, and we use an implicit Euler scheme associated with the characteristic Galerkin method. It follows the particle's trajectory in time and use the previous position as a node at which the solution is evaluated. To discretize, In order to space, we used finite element methods with elements P2 for the velocity and P1 for the pressure. We use also continuous P2 elements to discretize the tensor. The discrete system to solve is given by this set of the equations. The simulations are done in 2D computational domain, this type, which has the length and inlet and and outlet enough to obtain the fully developed flow. And here we can see some proportionalities that characterize this domain, and in this table we can see some details of these dimensions. We can see here some part of the mesh with the particularities of the number of elements and nodes P1, P2, and also the diameter of the elements, the maximum and the minimum of the elements used. No special treatment was used to symmetrize the grid with respect to axis. The model and the algorithm was implemented using the FreeFM++. To the boundary conditions, we use the wall no-slip conditions. This means that the velocity is equal to 1 in the rigid wall, in the up and down. And in inlet and outlet, we impose the exact analytic Poisson solution for the fully developed flow. We set some parameters in our simulations, like the polymeric viscosity is fixed with 0.1, as well the time step. We perform spheral tests for Reynolds in the range between 100 and 1000. And we use the continuation method in the Weissenberg number. This means that the Weissenberg number is increasing incrementally while taking the convergent solution obtained for lower Weissenberg as the initial condition for higher Weissenberg simulations. Or one of the quantities that we evaluated, it was the wall elastic shear stress, defined this way, where we have here as hat the outward unity vector and T as the tangential unity vector on the related to the wall respectively. We use the numerical solution was obtained considering a decoupled iterative algorithm known as Picard method and the time merging procedure. To stabilize the algorithm, we had an artificial diffusion term in the constitutive equation. Usually the researchers use the artificial diffusion term defined this way. This term is proportional to the Laplacian of the extra stress tensor with a small positive alpha. As alpha is constant, and in this case, this term is this way proportional to the Laplacian of the elastic stress tensor. And from now, I refer this term as the standard stabilization term. We can see that even we obtain the convergent solution. In general, this extra stress term doesn't vanish. So there are here explicitly adding something in the constitutive equation. So the same way this equation is modified, and we don't have anymore the original model. Motivated by that, we sought introduce a new extra term to stabilize the model. Such way, this term goes to zero when we obtain the convergent solution. And for that, we define this extra term proportional by the Laplacian of pseudo-time derivative of extra stress. So this way, when we obtain the convergent solution, this term goes to zero, so nothing is added to the constitutive equation, and in fact we expected to obtain the solution for the original model, or as I want to call, the classic Oldroyd B model. As the needed to stabilize the algorithm is greater than greater is the Weissenberg number, and the simulations here obtained by the continuation method with respect to Weissenberg number, we were motivated to define also a parameter alpha depending of Weissenberg, and this parameter was proportional to the square of diameter of the mesh multiplied by time step, and the arc multiplied by the arc tangent that is depending of Weissenberg. The reason that we choose something like that, it was because we want a parameter with two asymptotic values between 0 and 0.04. So the behavior of this parameter is here.
2 minutes, Maria.
Yes?
2 minutes, yeah. 2 minutes left, yeah, go on.
How many time?
2 minutes, yeah.
Oh, I need to be more. Okay, thank you. So this is the behavior, and we choose here the constant values alpha as the usual researchers done. So we here study the norm of the standard term, and we see that the values increase when Weissenberg increases, so and the values are significant higher, so some values are in fact added to the standard, to the constitutive equation, and we can see here that the value of the norm or Laplacian elastic tensor without stabilization are very higher compared with the same tensor for stabilization. And here we can see that the magnitude of the values added to the constitutive equation is very, very higher. So this introduces some differences in the solution, as we can see in the normal of the stress tensor and the shear stress tensor, and also the other component of the stress tensor. Here we available the maximum of the normal tensors or the normal components of the tensor without stabilization in green and with stabilization in the other colors, and we can see that this maximum decrease how much more higher is the value of alpha. This is very clear that the solution that we obtain for the standard is completely different. So we did the same for the other components, and we also studied the pressure drop, and the pressure drop is completely different when we compare without stabilization and with stabilization. So the same behavior for the velocity components, and we can see also the same effects for the elastic stress tension that decrease when the alpha increase. So for the term that we propose, we observe that the values when we obtain the convergent solutions are very small, is almost zero. So the magnitude of what we add in the extra stress in the constitutive equation is almost insignificant, and this doesn't see significant change in the solutions, as we can see in the components of the elastic tensor. And here we see also that the maximum of Q11 match completely in the case that we can compare it without stabilization, in opposition what happens with stabilization in the standard case. We saw the same for the maximum for the shear stress and for the other component also. So our proposed in fact match the solutions, and we are very satisfied with the results, even that we can see here some limitations, because we don't obtain higher Weissenberg's numbers as here, but in fact we obtain a solution for Huygens Weissenberg numbers, but in fact is not the solution that we want for the classic model, and we can progress a little bit, and we can believe that the solutions are good. So we study also the pressure drop for our case, and we can see that the pressure drop match completely, and the same for the wall shear stress, the elastic stress tension, independent of alpha. So we can conclude that the original formulation without stabilization becomes unstable for small Weissenberg numbers. So we need to introduce some stabilization to obtain solutions. And the standard stabilization, in fact, give solutions stables, but is not for the original problem. And we improve a little bit with this without changing the solution, and continue this work to try identify some limitations and improve our method. Thank you very much for your attention.
Thank you very much, for an interesting talk. Unfortunately, we do not have time for questions, so questions can be asked by chat.
Yes.
Okay. I will pass on to Joachim to introduce the next speaker.
Yeah, thanks, Michael. And please, Marilyn, can you stop to share such?
Of course.
Yeah.
Sorry.
Yeah, thanks. So, Cheryl, are you there? Yeah.
Yes, Professor.
Yeah, nice to see you. Welcome.
Thank you.
I don't know, I suppose you went to share your screen to show your slides. I suppose so. Yeah.
Yes.
Everybody is fine at Caracas State University, right?
Yes, sir.
And so on. Yeah, good.
Yes.
Yeah. So Cheryl is a student in UPGV in France, but she is teacher at the Department of Mathematics at Caraga State University in the Philippines. Welcome, Cheryl, and please.
Okay. Thank you, Professor Joaquim, for the invitation and also for this opportunity. So I will present part of our paper entitled Optimal Control of a Dengue Vaccine Model, Comparison between Vaccination and Vectorial Control. So in this topic, I will give you a short introduction on the dengue and then vaccine, and then present to you the model that we proposed and describe the parameters involved. And then from that model, we're going to present to you the control strategies and the optimal control and its conclusion. So dengue is the most common mosquito-borne viral infection found in tropical and subtropical regions around the world. In a study by Bott et al., predominantly in 2010, an estimated of 96 million apparent dengue infections cases globally, 70% of which is in Asia. It occurs in urban and peri-urban areas with peak transmission during the rainy season. Dengue is caused by 4 types of viruses, which transmit through the bite of Aedes aegypti and Aedes albopictus. In most cases, dengue is a self-remitting illness, but may require hospital admission, where supportive care can modify the cure of the illness. Infection from one type grants lifelong immunity to that virus strain and also appears to grant partial protection. But when infected for a second time with a different type of virus, a more severe form of disease will occur, known as this dengue hemorrhagic fever. Efforts to develop a vaccine against dengue have been ongoing for decades. The first commercialized vaccine is CYD-TDV, or also known as the dengue vaccine by Sanofi Pasteur. It was licensed in December 2015 and approved in 11 countries, including Philippines. In fact, in December 1, 2015, the commercial sale of dengue vaccine has been approved, making the Philippines the first Asian country to commercialize. And in effect, in April 2016, the Department of Health launched the dengue vaccination campaign in the Philippine region, involving more than 800,000 school children who receive at least 1 dose of the vaccine. The vaccine should be given or administered in 3 doses in 6 months apart. And it is a live attenuated tetravalent product made using the recombinant DNA technology by replacing the pre-membrane and envelope structure genes of the yellow fever 17D fever vaccine with those of the 4 dengue serotypes. So Sanofi Pasteur recommended that the vaccine can only be used in people between the age 9 to 45 and people already infected by 1 type of virus. So let me present to you our model. This is based on the Rust model. In here, SH, we call this as the primary susceptible human, or those individuals who have not yet been infected by dengue. And the delta S sub H is the secondary susceptible human, or those individuals who previously had dengue infection. We have the infected human, the recovered human. In here, the recovered human are those who have been infected by the 4 or who recovered from the infection of 4 strains. So SH is the susceptible mosquito and IM is the infected mosquitoes. For the human compartment, we know that primary susceptible humans becomes infected once an infected mosquito bites the primary susceptible human. So ABH-IMSH over H represents the infection rate of the proportion of primary susceptible individuals to be infected with dengue virus. And in here, BH is the probability of transmission of virus from infected mosquitoes to primary susceptible, and A is the average mosquito bites. So the same is true for the secondary susceptible. ABH tilde, SH tilde IM over H is the infection rate of the proportion of secondary susceptible individuals to be infectious again with different serotypes. So the BH-TLD here is the transmission of the virus from an infected mosquito to secondary susceptible humans. Gamma IH is the recovery rate of the infected individuals, and the delta IH is the recovery rate from all strain of dengue. In this study, we consider only the constant human population. So we did not care about the mortality rate of human. And for the dynamics of mosquitoes, susceptible mosquito becomes infected mosquito once it bites an infected human. So the ABM IHSM over H is the infection rate of susceptible mosquitoes to be infectious once it bites a ratio of an infected human population. BM is the transmission probability from an infected human to susceptible mosquitoes. And A is still the average mosquito bites. So we consider in here the mu-M, which is the death rate of the mosquito, since our growth function for the mosquito population is an entomological growth function. So from this ODE, we have the following result, which is, I'm not going to prove it. So the global wolf nest, the domain omega defined by this one is positively invariant, and in particular for an initial datum of omega, there exists a unique global in-time solution U in this function. And we get 2 disease-free equilibrium and also our basic reproduction number, wherein we can prove that if alpha M is less than the mu M, then E sub 1 is globally asymptomatically stable. And if alpha M is greater than the mu M, then and our R sub O is greater than 1, then our A2 is globally asymptomatically stable. We have to note that our A2 is actually, or has biological meaning. It means that it is an average number of new infected humans is proportion to the transmission rate due by biting during the infection period and the mosquito life expectancy. So based on that ODE, we can have these control strategies. In the control strategy, we have 3 strategies implemented: the vaccination, vectorial control, and the combination of both. But I only have here the combination. But if we consider only the vaccination, so we will not include this part and this part. And if we consider also vectorial control only, then we will not consider this and this one. The V sub 1 SH is the vaccination given to primary susceptible human. V sub 3 SH tilde is the vaccination given to the secondary susceptible. And the VMSM and VMIM are the vectorial control given to the susceptible and infected mosquitoes. So from this ODE, we have the results, or I mean, we consider from this ODE, we can have that the total human immunity is given by V sub 1 SH plus V sub 3 SH tilde, and the total vectorial control is V sub M SM plus V sub M IM. So from here, we can actually also get the global well-posed nest, and we have 2, again, disease-free equilibrium, and we can get this theorem from, we can show that the V1 is globally asymptomatically stable if our alpha M is less than the mu M plus VM, and our A2 is globally asymptomatically stable if alpha M is greater than the mu M plus VM. So from these control strategies, we use this as a basis for our optimal control, but we have to take note that in our control strategies, our VM, V3, VM, V1, V3, and VM are parameters. In our optimal control problem, we replace it by W1, W3, and WM, but they are now in terms of time. So they are in terms of time. So for the optimal control, we assume that both control inputs are piecewise continuous function and takes its value in a positively bounded set. And we consider this function j as our objective function subject to this condition. So from here, from this optimal control problem, we get this lemma that there exists an optimal control W star of this form such that our j is equal to the minimum of this one under the constraint that SH, IH up to IM is a solution of that optimal control problem. And also we have here the lemma that there exists an adjoint variables lambda sub I of the system following the backward in time system of the ODE, such that this one is has a transversality condition that our lambda of t is equal to 0. So we can actually prove this simply by using the Hamiltonian and then finding the derivative of that Hamiltonian with respect to our variables. And from that, we can show that our adjoint system is just the derivative of that Hamiltonian with respect to our variable. So another theorem is that the optimal control variables are actually given by this form, which is, we can prove this by the Potrogin maximum principle. We have to note that the Potrogin maximum principle is used to find the best possible control for taking a dynamical system from one state to another. So it states that it is necessary for any optimal control along with the optimal state trajectory to solve the so-called Hamiltonian system. So our Hamiltonian system, earlier, we're just going to use it in order to get this optimal control variables. So from those steps, we now use that to get our numerical simulation and using actually this algorithm. Again, it's just the same as what we did earlier. We solve the forward system, then the backward system lambda, and we get we update our W from this one. So from that, we get this result. Okay. So from this result, minimizing the infected human, we can say that the combination of vaccination, which is the blue one, the combination of vaccination and vectorial control is the most effective method. It takes you smaller time and lesser effort. But of course, without the control strategies, it takes longer, the red one. And for the vectorial control, it takes longer time, but slightly the difference between the vectorial and the vaccination is not that really high. So, but you have to take note, the most important part in this one is take note the secondary susceptible. As you have seen, vaccinating secondary susceptible humans offers few benefit compared to without control. So it's really, the vaccination of the secondary susceptible is not really that what's that? It has few benefit compared to this without control. Okay. So aside from that, we also have this numerical result for the primary susceptible human. Okay, of course, the vectorial control has lesser impact on the primary susceptible humans, but actually this one shows that it takes 7.5 days for vaccination and 14 days to combine vaccination and the vectorial control to reach the 0 primary susceptible individuals. Okay, and for the healthy human here is, we consider is the total immune or totally immune human, the TH, then the primary susceptible, the secondary susceptible, and the recovered human. This is what this healthy human population that we considered here. So this shows that the combination of vaccination and vectorial control is the best method in maximizing the healthy human population. Actually, the combination of vaccination and vectorial control is always the best method in this part. But if we're going to consider the optimal control, this is, we can see here that concerning the vaccination only, vaccinating primary susceptible human population requires shorter time compared to secondary susceptible. So for vaccinating primary susceptible, you have the W sub 1, is takes shorter time compared to vaccinating secondary susceptible. While in minimizing the mosquito population, the vectorial control method is better than the combination of the two strategies. So in minimizing for this part here, in minimizing for the mosquito, okay, as you can see, it takes shorter time for vectorial control compared to the vaccination. But the most important thing here, or the thing that's interesting in here, is actually this secondary susceptible. As you can see, it takes constant effort to vaccinate secondary susceptible humans. So for the conclusion, dengue vaccination or dengue vaccine is recommended to individuals who have been infected by one serotype of dengue. And we have shown that vaccinating only the secondary susceptible offers few benefits compared to without control, and constant effort is necessary. Our result shows that the combination of vaccination and vectorial control treatment is more effective. Thank you for your attention.
Thank you, Cheryl. Nice. So we are at time, no time to do some questions. Eventually, by the end of the session, if someone wants to ask, everybody, of course, can chat directly, or perhaps eventually at the end we can do it. So this is time to Mohamed. Are you there, Mohamed?
Yes.
Yeah. Welcome. Nice to see you.
Nice to see you too. Nice to see you too.
I suppose everything is fine with you.
Oh, yes, sir.
Yeah, everybody is here, of course. Okay, I suppose
Hello,
you want
Mohammed.
to share.
Oh, sorry. Michael, how are you? Okay.
So I suppose you want to share your screen.
Okay.
So
how to do is
in the bottom you have a green bottom share screen in the Zoom.
Partager l'écran.
Ah, ok. Partager l'écran.
Okay, so
Okay.
Professor Mohamed Geda from UPGV will talk us about some qualitative properties of red blood cell shapes. Thank you. Please.
Okay. Thank you, Joachim, for the invitation. Okay. My talk is, in fact, an introduction to red blood cell dynamics. Okay. This a joint work with Ala from Marrakesh and Huda Fahim from Amiens, and this is my PhD. And this work is a part of a big project, which, yes, we have some application for biomedical. In fact, the project is to understand the dynamic of blood, in particular in the presence of some virus, for example, virus COVID-19. So why blood? In fact, blood is a complex fluid, and in fact, we want to give some physical or mechanical explanation on the dynamic of red blood cell. Clearly in the microscopic level and also in the structure of macroscopic, for example, to understand the rheology. And of course, this is not an easy problem. One of the objectives is to understand, for example, the formation of embolism. And also, this phenomenon is also appear when when the person has COVID-19. So, in particular, we want to know to understand the transport trajectory of each RBC. And why this formation? Why this dynamics? And when I say why, in the sense that we have we want to give explanation from mechanical, not from medical. So here we present some these particles like red blood cell. In fact, the form of RBC is this one, is biconcave one, and usually we use vesicle. Vesicle is formed by it is a membrane, and inside is water with the viscosity, and outside is water, also water, but with different viscosity. And this membrane gives the form of RBC. In the sense that it's deformed, and you get different form. Here, we have initial form, biconcave disc, biconcave RBC, and in the presence of the fluid, this form, we obtain another form. And to understand the dynamic of each particle, we need to know, for example, the beta. Beta is the angle between the flow direction and the major axis of the RBC. And the dynamic of beta, or the evolution of beta with respect to time, we can obtain different dynamic or different form of the shape of the RBC. And numerical solution obtained by Omori is we work with Madame Barthez in Copian. They obtain three major different dynamic. The first one called the tumbling. Here the RBC or the particle behaves like a rigid part. Here, or here we have some different form or different dynamic. Here the RBC makes some small oscillation, but here we have a large oscillation. And the third regime or mode is called the Tantridian TT, in the sense that the major axis have a fixed orientation. And these two different dynamics have a very effect on the rheology of the blood. This is in the first here. Sorry, this is obtained from numerical simulation, but here is obtained from experiments, and here we have also different, exactly the same dynamic. The first one is TT. The second one is VB or trembling. You see that in blue, the major axis oscillates, but it's small oscillation. but here is a tumbling. We have the major axis, there's some rotation for every time. And this obtained by imagery from experiments. And the thing is very interesting is that the region, this mode, 3 modes, have in fact a strong effect on the viscosity, in the sense that here we have TT, and here we have tumbling, and you know, donc with some parameter lambda, I give the definition of lambda later. With some parameter varies from 0 to infinity, the viscosity change. So that means that from at level cell level, we have some mode or regimes, and these regimes has a strong effect on the ecology of the RBC. So why we this project, or why now we look for we want to describe the dynamic of every RBC. We will suppose that RBC is for one RBC, for example, to obtain different property of blue there. From numerical simulation or from experiment, we obtain 4 major parameters, which have a strong effect on the shape of RBC. The first one is delta X area, given here, where A is the total area of RBC. 0.1 is the effective radius. Lambda also plays a key role. Lambda is the viscosity relation between the viscosity inside and the viscosity outside. Of course, we have bending number and elastic number. And for example, for the human RBC, the delta X area is near 5. The problem is very difficult, very difficult, because there are some theoretical models, but only when delta is very small. And here we have delta equal to 5 is this means very large. But we can obtain some model in approximate solution. And here we gave some different shape of output. The first one is a trivial solution, a sphere, and we have the polite or biconcave shape, and there are also different shape. This is observed by experiment. The end of the problem is to obtain a mathematical model to describe this form. And the problem is not new. Another physical parameter is delta. Instead of delta is 2. Is reduced volume, and when 2 varies, we obtain also different shape. Okay, when 2 is small or equal to 0, for example, we have circle, or we have also oblate or plate shape. And this is without flow, this initial shape. So in my talk, I will give an equation to obtain this different shape, some classification of shape. The first step in this, or the first work in this area is given by Evans at home, who only use experimental data. And he we propose this function. In fact, this function depends on three parameters: C0, C1, C4, and R. And these parameters are obtained from imagery. We don't use anything. Only we take image and this image, and he obtain some approximate numerical approximate of C0, C1, and C4. And this is first motivation of this talk, because in general, shape has to minimize some energy. So events and use only picture or image. So in general, we use here Wilmore or general Wilmore-Alfred energy, in the sense that every shape has to minimize some energy. And to have a model or equation, we suppose that the membrane or the membrane is given by this function equal to H. Yes? And of course, is H, the capital H is the main curvature. And here, you know, xm is radius of the biconcave. So RBC also has a constant perimeter, constant volume and constant surface. Here we consider only two dimensions, so we'll speak about area and perimeter. Now, the idea is yes, to use definition of H, because we have a relation between H and small capital H and small h. If we define kappa, we obtain the equilibrium equation, and this sample, in apparence sample ODE, and we have to solve this equation with this condition. The first condition is trivial from here is trivial, but here xm is not known a priori. So we have to find the solution of this equation and xm. Here p and r, a as r logarithm multiplier, but in fact p is the difference between inside pressure and outside pressure. So p and r in general are given. Are given by experiment, but here we suppose that p can be arbitrary. So this equation is very simple, but the problem how to solve this equation, how to obtain at the exact solution, maybe the solution to explain the form of initial shape of RBC. And also to have some to understand the effect of P and A, not on the existence but on the shape of the RBC. Of course, here xm is not known. We can, for example, this no autonomous equation, but if p equal to 0, we obtain an atomic equation, and in this case, the equation is very easy to solve by using phase plane method is okay. So now we have to suppose that p is different from 0. Of course, the model or the method is to use shooting parameters. So we add this new parameter, and we look for different value of parameter to obtain a biconcave solution. Wow. Okay. So the main result or term is the following. if we suppose that P and are positive, such that P satisfies this condition, so we can obtain a family of biconcave solution. The proof is very intuitively because in the beginning we don't know how to. Yes, of course we can obtain some numerical solution, but we have we have to obtain really analytically the result. In fact, this theorem is known before because there are some paper who say that when P over A power 3/2 is small, we can obtain solution. Here we obtain the exact condition on P A, and we for our study we suppose this is obtained as sufficient condition, but not necessarily. That if we take kappa prime 0 less than P over A, we can obtain these three different family of solution. The curve here blue is.
Il est 12 heures.
Oh, okay. The curve is this limit for our analytical result, not for exact, because you can obtain a solution even if this condition isn't satisfied. So here we include only three solutions, and in fact, what is remarkable is that this condition is equivalent to less than 0.7. In the case we had here, and here we obtain, of course, oblate solution, and also if we p equal to 0, we obtain the sphere. In fact, this is a trivial solution, and I suppose that in here, this solution, in fact, does not satisfy the boundary condition, but maybe this solution gave this one. So we are sure. So this is IDC and introduction. This is in the beginning. This is an introduction to basic dynamic. Of course, there are some mini result, analytical result about the evolution of the shape of RBC when t goes to infinity. So this is a small or introduction to the dynamic of RBC. Yes, I have no time to speak about what the junior result. So I think is time. I stop here. No, I stop here. But we have a numerical solution in 3D.
Thank you very much, Mohamed. So if someone has some question, please chat directly to.
Yes, with pleasure. With pleasure.
Okay. Please, could you stop to share your screen, Mohamed, such that Youssef. So this is time for Youssef Mamri.
How to do?
Tu bouges en haut, tu as arrêté le partage.
Ah, ok, merci. Oh, purée.
Okay. So, welcome, Youssef. In fact, Youssef is my front face, but a little bit at my left. Okay. So this is time to Youssef. Please, Youssef, could you share your screen? So, thank you to be here. Okay, yeah, 3 minutes of delay, but please, Youssef, let's start.
Okay, so thank you. Maybe you can cut also tu peux enlever le son, parce que sinon, tu m'entends 3 fois. Okay, so thank you for being here. So thank you very much, Michael, for sharing the session, and thank you, Joachim, to actually initiate all the session we organized So during so my talk is not you will not find a lot of mathematics in my talk. So there is some PDEs, but this is mainly let me check. So this is mainly multidisciplinary work with my collaborator from the National Institute of Research in Agronomy. I don't remember what is the E. So with so just to maybe to explain how multidisciplinary it is. So Sylvain is physicist. Nicola is a computer scientist. So Anne-Marie and Ronan are the ecologists. I am the mathematician. And Johan, so Johan was the PhD student, so he's the one who did the real job actually. So Johan has to deal with. So Johan is his formation, his background is in ecology and biology, so he has to deal with people from physics, from mathematics, from computer science. So it was a very interesting project. So in my abstract, I think I say I can explain things also for some pathogen and for other kind of insect. So in the short I have, I will speak only on this on one pest. So mainly what we are interested in this project is to model flying insect, and what we are considering is different kind of competition. So we are interested in flying insect. Those flight is so they are not moving only randomly. So they are moving with real movement with a high dispersion direction. So because we are working for the in RAE, so we are interested in agronomy. So we are interested in the crops. So we are not just looking on flying insect. We are looking on flying insect who create damage on crops. Where we have also some feeding place and having a seasonal activity, so depending mainly on climate. So this has to be seen in the insect movement as a competing resource. Why the insect will choose to fly, why so damaging, why he will want to feed, this is the laying. So why he will choose to lay, why he will choose to feed, and why he will go to wintering. So once we have this model, the second question is, can we use this model to test some strategies without pesticides, if possible, to limit the pest damage. So, and one strategy is by reorganizing the landscape. So, as I say, so the one goal is to search on alternative strategies so reduce the use of pesticides. So one of the first also why we start to work on this was because so theoretically in Europe and in France, so they I don't remember exactly the names of some of pesticides are now forbidden, and they are planning to stop in our dream, I would say, all the pesticides, but so it was one question. If some pesticides are forbidden, so we have seen the emergence of all species or some species that were not well studied. So we need to do some modeling. So what we say by reorganizing the landscape, so you can, so there is some policies, so you cannot do what you want. So mainly what we are considering is, so you don't change the geometry of the landscape, we just change the composition of the field. So what you put inside the field. And we allow us to also to have some change in the geometry. So changing, for example, some edge by so you can rotate a little bit the edge or something like that. But because there is some political policies, again, you cannot change everything as you want. So to assess the landscape and also to minimize the pest damage. So what we need at the end, so we need a model of population dynamics. So we need to describe the dynamics of the pest, of the insect. And also we need a model of landscape. So I think I will not have enough time to describe very well the model of landscape. So, but I will insist more on this. And then you have to link these two models. So mainly the movement of insects will depend on the landscape. So with the enemy we are looking for during this talk, so this is the cabbage fly. So in the state we were studying this, so cabbage is something very important for the state, for the agriculture of the state. And so this is the enemy. So this is a fly, so it's a Latin name, so Delia radicum. So here I put his CV, his resume. So he's an expert in brassica. So brassica are mainly the cabbage or species or same species. So what he is doing in brassica, maybe now you will be, so that's why you have to clean, to wash your cabbage when you buy some cabbage. So the cabbage is mainly the laying sites. So he's using brassica and also cabbage for his larvae, mainly for laying, and the supply sites or the feeding site are the edge. So you imagine you have your landscapes, you have some field with cabbage, and you have the edge, and so loosely speaking, so the fly will feed inside the edge, follow the edge, see some cabbage field and lay and reproduce in the field. So sometimes we use, yeah. So there's some colleagues who are expert in insect psychology. So this is important. So they want to know, so mainly they want to know what wants an insect. So but mainly, I would say like humans, they want to, maybe more men, they want to have food and they want to reproduce. So this one is present in almost every country in Europe. So what is the life cycle of the cabbage? So the adult will lay on cabbage field. So sorry, it's written in French because it's coming from a PhD thesis from the INRA also. So the eggs, so you will lay on cabbage field. So they have, yeah. So the life cycle is more or less 6 weeks. So you have 3 stages of larva A. So the larva A will really destroy the cabbage. You have one last, so this is not anymore a larva A, this is a nymph, but sometimes we call it a pupa. So I think in the rest of my talk, I will call them pupa. And then you have the adult stage. So mainly, so only the adult will travel, will move in the field, and the young one will stay inside the cabbage field. So yeah, so the adult will travel inside the landscape at the landscape scale, and the young ones stay in the field. Okay. So what is the objective? Our objective was to build a spatial temporal model to regulate pests. So not only, so we use also this one because we have a lot of data. I will show you later. So our goal was not to provide statistical model, but a mechanistic framework in order to modify easily the landscape and see the interaction with the insect movement. And so see the role, so you can imagine of two things, the laying site and the feeding site. So what is the role of these two places in the invasion? And then can we deduce new strategies, and the spatial temporal strategy to control the pests? So what I will do today, so my introduction was very longer than my talk, maybe. So what I will explain is how we build our model. So I will try to do it in details. How we get all the parameters, how we calibrate our model, and then how we use it on different landscape. Okay, so just to explain, so what is so all the illustration were done by Johan, the PhD student. So what we want to do is to take into account the individual behavior inside a landscape. So we want to go from the individual behavior to the population behavior. So when you are looking to the landscape, so what is done mainly, so if, so imagine I am a fly. So what I will do, I am in the landscape, I will look around me, what I can see. So I will look for the resource around me. So I will use my resource perception, what I see around me. So the green edge are the feeding sites, so, and the orange one are the laying sites. So I'm looking around me, what I see, for example, I'm here, so I see I have some feeding site, I have a laying site. And what I will do, okay, if I have eaten enough, if I have enough energy to travel, I will travel. I will mainly go to the laying site. If I don't have enough energy to move, I will go first to the feeding site. So this is what we call the energy allocation. So maybe I'm looking around me. If I need food first, I will go preferably to the feeding site, take enough energy. I have enough energy. I'm going to the laying site. So I think this is when we present this the first time. I think it was more or less new way to see the thing. There's some similar things that were be done, but so instead of considering energy allocation, so you are looking for what is around you, your perception, and there is some model of risk. What is the risk to move from this place to Joachim? Joachim just yes, so I think it's safe to move to Joachim. Maybe this is now too far. Maybe it's not so safe to move to Nabi. So there exists some model when you are considering the risk to move. To our knowledge, before us, there is no model with the energy allocation. So we have to translate this into PD. So as I said before, we want to do some mechanistic model because we want to see what is the impact of the landscape and something. So what we choose is a spatially explicit reaction diffusion equation. I will explain how we build the diffusion, the dispersion. So we need to take into account the dispersion. So just for people who are working on dispersive equations, so the dispersion in terms of ecology is more or less the diffusion and not the dispersion in terms of mathematics. So we need to take the dynamic the life cycle of the insect, and we need also to take into account the dynamic of the field. So I think I will not have enough time to explain what we have done for the modification of the space or the dynamic resolution of the landscape and what we will do later. So what is the main assumption? So I think, so maybe some of you will not agree with that, but so this is more, I think in ecology, because so I've talked a lot with ecologists, so this is more, let's say, philosophical than, there is no real proof of that, but we use this assumption. So I don't remember exactly the date. So we say that the main driver of the dynamic is the foraging. So this is what I said before. So if I need food, I go to the food. If I need to produce, I go to the laying site. So this is not what does it mean? It's not a random walk, as I said before, but we are not interested in a fully random walk. So this is a bias-based random walk. So you want to go somewhere. So you are looking around you. If there's nothing, you move randomly, but you have some preferred direction to move. So this is the foraging. Okay. So, and we can translate this as a reaction diffusion, advection reaction diffusion model. So I will explain how we build that. So, and as I said before, and I will certainly repeat again. So what we want is a model where the population is very sensitive to the landscape change. So we need to take really into account the landscape in the population dynamics. So how we do the population dynamics, this is quite standard. So you consider the life cycle. So this is, I guess, the same I put before. So, but as I said, so you have the adult stage. So adult will lay. So you have the eggs. Eggs will become larvae. So to simplify, we put only one stage of larva. We can put the 3 stages. This is not so difficult and not so important. Then you have the nymph stage. So as I said before, now I call it pupa. So you have 2 types of pupas, what is in diapause and in non-diaposing. So in diapause, it means the one who are wintering. Okay, so during a cold season, they are wintering, and during the spring, they become directly adult. So they stay in this stage inside the soil. So I will not explain also there in this one, but one strategy to control the pest is also to use to deal with the soil. So you made some modifications. So maybe if you have a garden, people say you have to take the land and mix again at the end of the winter, for example. So we can take into account the soil, but I will not explain. Yeah. So we need to translate this into equations. So this is quite standard. So maybe if we just see, for example, first the equation of adult. So this is here, the time derivative, the variation of adult. So as I say, you have the plus, so you have the pupa in diapause plus the pupa from the life cycle. You have here, yeah, I didn't put exactly, so let me just, yeah, I put, no, I didn't write what is, so gamma is the transfer from one component to another component, and omega is the death rate. So I will come back later for this one. So you have a mortality. So omega is the mortality rate for each stage. So maybe it's easier to see. So here you have an oviposition rate. So adults give birth to will lay. So adults are laying. So the parameter here. So maybe I should start at this. So T is the time, X and Y the space, and theta is the temperature. This is something important in ecology. So adults are laying. So then you have the mortality rate. Here you can see you have the transfer egg to larva. So egg to larva is here. So egg are becoming larva. Then you have larva that are becoming pupa, etc. etc. So sorry, sometimes I shouldn't have the N here, etc. etc. So here we have the equation for adult, and here we need, so as I said before, so only we are looking only on the movement of adult. So only the adult will move. Yeah, this is the thing. Yeah, so temperature is here. So for adult, I say also, so we have the time, the space, and also the energy, allocation of energy. So I need energy to move. Okay, so what I need now is to compute the movement and the energy allocation. So how it can be done? So the simplest way is to consider a diffusion term. So the diffusion will depend on space, it depends on the landscape. So mainly the first one is the perception of resource. I'm looking what I have. So this is the simplest model, just to explain. So the perception, what we call kernel of dispersion also sometimes. So I'm looking around me and I move. And then I have an advection in the energy. So if I am, I will explain it a bit later. So if I am feeding, my energy is increasing. If I am, I cannot lay, but if the insect will lay, his energy will decrease. So we have these two components. So the question is how to define this diffusion or dispersion coefficient and the allocation of energy, the energy budget. So we need to so this is why also this is important to have, as I said before in my introduction, a group with a very wide competence. So because now the technique is mainly coming from computer science and from image processing. And Nicola is our computer scientist, is an expert on that. So the perception, you can see the perception so from your discretization in space, or what you do, okay, from one point, you are looking what is around you. So mainly here, from this point, you see you have a feeding site, and here you have nothing. Well, if I am here, I will have the laying site. Here I can see a feeding site. If I am here, there's nothing. So mainly, if I am here and I need food, I will go to the feeding site. If I am here, I need energy. Even if I am close to the laying site, I would prefer to go to the feeding site. If I am ready, if the insect is ready to lay, it will go there. If you are in the middle of nowhere, you will move randomly. So you don't know, you don't have any preferred direction, so you move randomly. So what we use is inverse distance whitening. So what is present here is a tense filter. So sometimes we use a Gaussian filter. So I think just the slide after I will put the Gaussian filter. So in the beginning, so especially during the thesis, Johan tried many kind of filter to see what is the most relevant one, the most natural one. So it looks like for the flies, the best one is the tense filter. So this is something well known in image processing. So in terms of mathematics, sorry, so it is translated as this. So you have here the Gaussian filter. So I use mainly exponential filter. So you can put also with the square to have the real Gaussian filter. So what we do is, okay, you have so the perception is decreasing exponentially fast with the distance. So, and the coefficient gamma is the what we call the, so this is mainly the distance where you don't see anything. You cannot recognize anything. So we do that for every laying site. So we have, so actually the coefficients are not the same for the, are the same. The same for the feeding site. Then you can build, or you can create a gradient. So here there are some normalization function. And then from this, you define your dispersion or diffusion coefficient. So what you have is actually, as I say, so if you have nothing, no preferred direction, you will move randomly with a constant diffusion. Here you have two different weights, so depending on your energy. So here, if you need food, you prefer to go to the food. If you have enough energy, so the so the energy is between 0 and 1. So we build our model such that the energy remains between 0 and 1. So if you are if U is close to 0, so you will prefer to go to the feeding site. If U is close to 1, you will prefer to go to the laying site. So again, so I show you mainly the last result, but we had a lot of work to compute what is the good weights to take into to put in the equation. So how we now build the energy supply, so the advection in energy. So if you are in the middle of nowhere, when you move, you lose energy. So because you need to move and you need to, so what is the coefficient? So the coefficient is just so the advection term, if you prefer. So this is a constant coefficient and negative. So if I am in a feeding site, my energy will go up. So now I have a coefficient, a positive coefficient. So, and in the laying site, so you need energy to lay, so your energy will decrease. So sometimes we put also a carrying capacity in the field. So actually, what we have seen for the cabbage fly is that this is useless. We don't need to put the carrying capacity to have enough result. So just to show you how it looks like. So because I cannot see very well here. Okay. So just to show you. So when you have the same weight for feeding and laying, so just saying okay. So sorry again, because in our notation, so E is the U is not, so E is the energy, and so if you have few energy, so one, so this is our disputation. So if I have few energy, you see the arrows, you go preferably to the feeding site. If you are full of energy, you go preferably to the laying site. So this is what's happened. So this coefficient is, so we don't know exactly what to put. So later we did some statistics, but just to see what happened if I say laying is more important than feeding. So it's just, so the distance, so no, it's not the distance, it's just the strength. So you will go preferably to the laying side and to the feeding side. So okay. So finally, so we have a system of so we have 1, 2, 3, 4. So 4 ODE and 1 PDE. So that we need to calibrate. So this is something. So the good thing is that we have we have data from the field, but we don't have a lot of data. Okay. So what you see is the blue dots are the sampling location. So this is mainly on the inside the bicycle. So they have some trap, and they count the number of flies. So one question, so one thing we ask them is maybe this is not a good place to count the insects, but anyway, so we have access to the all data from this location. So to calibrate the model, so what we did is, so we take the data from the previous, so I don't remember which, I think it was 2010, and then we parameterize with this with 2010. We run the simulation for 1 year, and we compare with the data. Again, so we have a lot of parameters that are depending on the temperature. So we have access to the local temperature, we have climatic data. So the change, I mean, so the change from the eggs to larvae, so larvae to pupa to adult, all these things depend on the temperature. So again, it was a huge work done by Yohan to find what is the best formula to compute, for example, so I think I have also the oviposition, so no, it's later, to compute, for example, the change from eggs to larvae. So mainly tried a lot of things, and he was able to select. So just to show you, all of this function look like this type of equation of curve. So this is this axis is the temperature. So mainly it says so you have an optimal temperature to have more and more insects, for example. Okay, so from the data, we compute this kind of thing. Okay, so one other thing, so mainly this one were already known in the literature. So mainly we just took what is in the literature, and we compare. What was not known is the oviposition. So we say the oviposition depends on the temperature, but we don't have anything in the literature. So what we did is, so we take the data, the experimental data, and we try to fit some curve. So if you, so I know this is very fast, but what is here? So the function is here. So in ecology is quite standard, so, but this is mainly a combination of this kind of function. So it was not so easy to find all these things, but we did. Okay, so we have this thing. So just to show you, maybe 3 minutes. No, it's okay. So just to show you how we did the simulation. So we have this GIS file. So we select only what we are interested in. So the feeding site and the laying site. As I said, the data from the previous year are used as initial data and the calibration, and then we run the model. So just to show you what happened, yes, also April 2011. So this is the kind of thing we have. So okay. So just to show, okay. So, because I have, yep, I will do it like that. So mainly what you see is that you have a lot of, most of the flies are here. So if I just come back in my field, so this is the biggest laying site. So this is more or less normal. So I don't know if there is a very good expert in pest invasion in the audience, but if there is a very good expert, he will say this is not totally realistic. So, but I will not explain that. So we did some sensitivity analysis to see what is the important thing. So what was important is that this is not only, so there's two important things, or as I said, so the energy and the mortality are the most important thing to control the pest invasion. So mortality, okay, you can use pesticide, or if you want to control the energy, you just need to modify the landscape and the age, maybe. So just to simplify, yeah, maybe I will not explain. So still, I say there is no mathematics, but you can do a little bit of mathematics. So it's not so trivial. It looks like, so just to simplify, we put all the Young in one component just to simplify. So you have an integral differential equation. You can prove that you have a global solution. So one trick is to remove the energy, so is the U. So you can remove the energy by this change of variable. So you have a non-linear parabolic equation with, so you can have jump in the diffusion. So, but it's quite standard to prove local robustness. So what is not so, if you find the trick, it's simple, but it took some time to find the trick. So you can rewrite the equation by some bootstrap to have kind of ODE to solve recursively. And you can see that, okay, step by step, maybe it's not here there's a private joke with a step by step. And then you can use standard Gondval lemma to prove it. Okay, so I will not explain the optimization, but just to show you that if we can modify the landscape, if we modify the landscape, so maybe I will just show the final result. So as I say, I was sure that I cannot explain the model of landscape, but just to say, okay, if we have, imagine you can do 5% of change in your landscape, as I said, so in terms of composition, or in terms of just you can change, it's just changing in the composition. This means you change what is inside the field, or you change an edge by something else. Okay. So what we say, so this is mainly, so what we can prove is that, so what we can give is an optimal procedure, saying, okay, you take your initial landscape, you say, okay, we allow 5% of change, and in 83% of, so, and sorry, maybe I will explain. So you take your initial landscape and you allow 5% of change. You run the optimal procedure, it will give you a new landscape in terms of composition. And in 83% of, so we did that for, I don't remember how many landscape. So we always have, so we reduce the pest invasion of 30% for 83 of the modified landscape. So finally, with this model, we are able to, so sorry, I have not enough time to explain the landscape, but combined with maybe I can conclude. So the model we developed, so we have a mechanistic model of invasion combined with a model of landscape, and we can offer an optimal procedure to modify the landscape and reduce the pesticide. So again, see if you are in ecology, so the assumption we take into account to say what is the optimization process for what wants a species. So this is also philosophical. So for us, so we use again the optimal foraging strategy. So what wants a species is to optimize his youngness. I don't know, maybe it's changed a little bit. Actually, in France, it changed with COVID. We want to optimize the oldest, I think. But so here, the optimization consists in optimizing the youngness. So what you want to do is to avoid a population to optimize his youngness. So the model is able to do that. So what we are doing now is, okay, so is to see what happens if you respect to the soil quality. So this is very important not especially for this species, but for the other species I mentioned in my abstract. This is very important because this is another species. This is a wire worm who can stay many years in the soil, and and also he loves every kind of thing. So one other challenge we are looking for, and normally we should start a PhD. So what we use is the temperature, the global temperature given by some thing. But what is actually important is the temperature below the field. Okay, so this is very important. Okay, so the some other thing we are doing is okay, I will stop there. Oh, I'm good. I know it's 45. Sorry, I have 1 minute. Okay, I will stop the.
Okay, thank you.
So sorry. I would like to thanks everybody who attended our session, the people outside, and of course the speakers. Unfortunately, we don't have the opportunity to meet in Portugal once again, everybody together. But well, let's try to do it as soon as possible. Thank you to be here. Thank you to all the participants. Thank you, Michael. Thank you to everybody.
And thank you, Joaquin, for organizing
someone
the session. Yeah.
To ask something. I suppose that the organizers want to finish our session, but please write us. Yeah, let's try to work.
Okay. And thanks, Joaquin, for the invitations and then for everything for organizing it.
Sorry, Michael, we didn't hear you because.
Oh no, I just wanted to thank Joaquin for organizing this session because he's done all the administrative work. Yeah.
Thank you. Yes, Michael. Sorry, I lost my connection. Yeah. See you, everybody.
Okay. All the best. Bye bye.
Au revoir.
Au revoir.